There we go. Okay.
All right. Our next speaker is Kavya Chopra from ETH Zurich. I'll give you 5 minutes and 1 minute. You have 5 minutes left and 1 minute left.
Okay, sure. Let me know when to start. Yeah. Hi everyone, my name is Kavya. Today I'll be presenting my work, Semantic Reification, a new paradigm for random program generation. As we all know, compilers are huge, complicated pieces of software, and sometimes things can go a little wrong. Your compiler may cause your program to hang, miscompile, or even crash. And these optimizations, while they improve performance, they occasionally introduce bugs as well. Now, differential testing gives us a simple oracle to find and snuff out these bugs in programs. You take a program, you have a reference compiler, and you test out the same program at different optimization levels with that compiler. If the outputs differ, something's amiss, and you have a bug on your hands. Now, differential testing itself is easy, but the hard part is actually generating these random programs. The thing with generating these random programs is that if your random program accidentally happens to have UB, the compiler can do anything, including making the proverbial demons fly out of your nose. However, what we want to do over here is generate random programs that are A, syntactically valid, B, UB-free, C, deterministic, and still nasty enough to test out and stress test the gnarly regions of your optimizing compilers. Now, previous work in this area falls under a paradigm that we like to call syntactic reification. C-Smith and Yapgen are fantastic tools that have successfully found hundreds of bugs across GCC and LLVM. They work under the same premise, which is you have a context-free grammar, and then you generate statements from that grammar. Now, you have a program which you feed back into a layer that filters out for UB in these programs. A couple of iterations of this loop back and forth, and you finally have a valid C program. However, despite these generators being extremely powerful, this UB prevention layer often causes some restrictions. For example, C-Smith has conservative analyses and runtime guards to help it avoid undefined behavior. Yapgen constrains loop iterations so that they all behave predictably and in a similar manner. These existing generations miss unbounded loops and irreducible regions. Unfortunately, these are precisely the kind of constructs that are notoriously hard to optimize and reason about and make compiler writers stay up at night. It is these kind of constructs that we also wish to model in our programs. Arbitrary control flow is our solution to having both these kind of constructs in our programs. Now, we don't just want arbitrary control flow because it sounds good, but because it's integral to testing out optimizations such as loop invariant code motion, code hoisting, code syncing, value numbering, IV ops, and so much more. We have harder, these are all important because these optimizations help track how values flow through CFGs. So when you make your CFGs arbitrarily more complex, it gets harder for the compiler to reason about these optimizations as well. And this is exactly the kind of thing that we want to test out. But again, it's very, very hard to generate these programs with arbitrary control flow. So the million-dollar question becomes, how can we generate these programs with arbitrary control flow while still guaranteeing correctness, definedness, and termination? Our solution to that is a paradigm called semantic reification. Some semantics gets thrown around a lot. So what exactly do we mean when we talk about semantics? We talk about largely two kinds of semantics over here. A, compile time semantics, which is what a program can do and what your compiler has access to. B, runtime semantics, which is what your program actually does at runtime. To model both of these semantics, we have proxies. Firstly, we have the CFG skeleton G, which is the CFG of a program stripped bare of its statements. So effectively a bunch of nodes and a bunch of edges. To model the compile time semantics. To model runtime semantics, we have an execution path pi of this program, which is just the path pi sampled through this graph. Then we put both these inputs into our magic semantic reification synthesizer, and out comes three things. Firstly, a program P. Secondly, a program input I. And lastly, a program output O, such that the CFGs of this program P has the same skeleton as that of G, our input CFG skeleton. Executing P on this program input I makes it follow the execution path pi and ensures that the execution is UB-free and terminating. Lastly, program output O. Executing P on this program input I ensures that, that the output we get is the program output O that we give you. So the key capabilities of semantic reification are threefold. Firstly, we give you arbitrarily controlled flow, because now you have full control over the CFG skeletons you wish to feed in, over the execution paths you wish to feed in. Secondly, guaranteed semantics by definition. And thirdly, an established oracle. Whenever you put this like input I into your program, you know exactly what's about to come out. Now, we proceed to do this using symbolic execution. And this begs the question, hey, how can you generate whole programs using symbolic execution? The path's going to explode, your SMT formulae are going to be really large, and the program is just, and the generation is just not going to scale well. To solve that, we decompose our program writing into two parts. Firstly, we generate functions that are small enough that they can be given, that outputs are tractable enough to be like obtained from these solvers and symbolic executors. Then we compose these smaller functions into larger programs using something that we call peephole rewrites and call graphs, something that I'll talk about during the later half of my presentation. So the idea is to use semantic reasoning where it matters and to optimize for scalability where it doesn't. Our implementation of semantic reification is a tool called Reify. Reify is a 5-step tool which first generates CFGs, samples a path through them, creates a symbolic function, concretizes it, and then uses many of these symbolic functions and composes them into whole programs. I'll walk you through an example of precisely how we proceed to do this. Firstly, we generate or borrow a CFG skeleton. Graphs are available on the internet aplenty. Real-world code has a lot of CFG skeletons. You can either take it from them, or you can use our in-house graph algorithm. All we had while generating graphs for ourselves was like was modeling basic blocks as nodes and edges as possible control flow transfers. Our soft constraints was just keeping the graph usable so that it doesn't turn into spaghetti code. And our hard constraint was that the entry and exit should have a path that connects both of them so that we have at least one valid value of pi to feed into our generator. This helps us guarantee arbitrary control flow. Second, we sample a runtime path through the CFG. For this particular example, we're sampling the path entry, B1, B3, B1, B2, and then the exit. The path says what the program actually does on this input. This enables arbitrary execution, including loops, repeated blocks, and any path as convoluted as you can think of. Thirdly, we create a symbolic function. Cool, we have a CFG skeleton. It's time to fill it in. The initial IR we used to fill in these functions was sim_IR, which was a minimalist IR that had addition and multiplication for 32-bit C integers. We've expanded the scope now, but let's keep it to this for now. Now, you'll see on the statements that there's multiple symbols over here. You'll see int a equals S1, C equals S2. A, B, C are variables. B1, B2, B3 are basic blocks. We understand that part. But then, what are S1, S2, and S3? Well, S1, S2, and S3 are knobs that you give to your solver. Currently, the symbolic function that we had in this slide was a program template and not a program itself. When we have S1, S2, and S3, we can use these to write our constraints that the program should follow and then feed them to an SMT solver. These are knobs the SMT solver will control and tell us what the value of these should be in order for our program to give us the guarantees that we promised you. But how do we actually go about generating these constraints? Well, you have a symbolic function, you have a path. How do you generate your constraints? Quite easy, actually. You just unroll your symbolic function along the chosen path. For example, let's take the subpath B1, B3, B1, and B2. Initially, all variables start off with their initial values, A0, B0, C0. Look at block B1. When you're assigning to C, its value gets bumped from C0 to C1. And similarly, look at B3. After B1, we're going to B3. We now have C1, A0, and B0. B3 assigns to A. So now A gets bumped from A0 to A1. Similarly, when we go back to B1, we now have C1, A1, and B0. And when we're bumping C again, now we bump C from C1 to C2. And the value for A we use is no longer A0, but A1, as was initialized in the previous block. So in the CFG, the blocks are the exact same, but there are different moments of time. And this is exactly what we wish to capture with these subscripts. Then we generate the constraints for our unrolled path. We have largely 3 categories of constraints that we would like to focus on. Firstly, definedness. These are the constraints that actually help you evade UB, including but not limited to integer overflow, division by 0, and the like. For us here, A naught S3 plus B naught S4 plus S5 and all sub-expressions of it should fall between int min and int max for the refiner's constraints to hold. Secondly, computation. We also wish to respect the operational semantics of the C language. So if C is indeed being assigned as A times S3 plus B times S4 plus S5, we wish to respect that and encode it in mathematical language as well. Lastly, and this is the constraint that distinguishes us, termination. Termination helps us mold exactly where we want the program path to go. We want the program to go from B1 to B3. Sure, C1 times S6 plus S7 should be less than or equal to 0. This is what can help us ensure that the edges we want exactly are taken, and this is what helps us ensure that the program exactly follows pi. Now, voila. Feed all these constraints to the solver, and you have an output. Now you have an output for all the symbolic values that you initially wanted. You put them back into the program, and now, hey, you have an actual symbolic function, a program input and a program output, with the guarantees that these are UV-free because of our definedness constraints, terminating because of our termination constraint, and follows pi again because of the termination constraints. Now, how do we use these smaller symbolic functions to generate whole programs? You have a random call graph, and that can be used to link functions. For example, main here calls func. So how do we link both of them together? Well, you know the output of func on a given input, so you just do some offset addition. So for example, func on this input gives this output, which in turn added with like int max minus 1 gives 32. This is exactly what we substitute in here. But hey, why are we doing these peephole rewrites in the first place? Aren't smaller functions sufficient to test out optimizations? Well, there's a lot of inter-procedural optimizations out there that we also want to hit, and this is precisely why we do this. And here's the kicker. The example that we've been walking through all this while was an actual real GCC wrong code bug that we found. This was because of some errors in the scalar evolution and IV opts passes. In terms of bug discovery, we've had 59 total bugs with 57 confirmed and 27 fixed. Recently, we found more than 15 additional bugs in GCC and LLVM. What kind of bugs did we find? Well, we found long-latent bugs, we found high-priority bugs, but more importantly, we found bugs that exercised complex control flow and exercised diverse passes in the compilers. Now, the coverage that we have is complementary to existing tools. You'll see that newly covered functions mainly involve inter-procedural optimizations, shout out to peephole rewrites, and CFG transformations, which is something that we claim as our own unique contribution. The reason existing tools missed these bugs was because they were a little conservative with the static analysis, runtime wrappers, no irreducible loops, and identical loop iterations. What we provide uniquely is arbitrary control flow with unbounded loops and irreducible regions. This is what makes me believe that semantic reification is a very promising complement to syntactic reification and has great probability and propensity of catching bugs which syntactic reification has not caught yet. To really hammer the point in, here's a small bug example that shows irreducible control flow. You'll see that block K over here is an irreducible region. And this is something that syntactic generation could never have generated for us. So this is our unique contribution which helped us find a bug in this particular domain. In terms of implementation and some stats on scalability, Reify has 7,000 lines of C++ and uses C3. Currently, we only supported C with 32-bit integers and arrays, but we're expanding. And we also ported to Java bytecode and were able to find 3 bugs in OpenJ9. The SimIR that we have developed is language agnostic. In terms of performance, the majority of the time, of course, is taken by generating the symbolic functions because the SMT solving takes that long. But we have, of course, minimized the impact of that using our whole program generation, which we do using peephole rewrites and not symbolic execution. Beyond the paper, we have refract-IR, which is a work-in-progress extension of SimIR. We now have first-class symbols, arbitrary precision integers, floating points, vectors, first-class intrinsics, etc. Reify's free implementation based on refract-IR found 10 bugs in GCC and LLVM within 1 week of running. In terms of future directions, we see this work going twofold. Firstly, implementation improvements, which is a richer feature set for refract-IR, and just faster solving for SMT. In terms of scope, though, we don't think semantic reification should be limited just to compiler testing. We feel that it can be used to validate static analyzers, debuggers, program verifiers, languages, runtimes, and the like. The key takeaway is that semantic reification makes program generation less about hoping for interesting behavior and more about constructing it with guarantees. Thank you so much. I'd like to welcome any questions now.
All right, questions?
Hi, thank you. Great talk. James Lee Jones from Imperial College London. So I can imagine that generating programs in this way can be fairly slow if you're relying on SMT solving. And I wonder if you considered combining this with techniques, which actually I think from your group, like equivalence modulo input testing, so that you only do the slow sort of generation once, and then you get the extra benefit of generating more programs and not having to go back through the SMT solver. And I guess also just one clarification. So I think you mentioned somewhere along the way that you avoid generating undefined behavior on the path that you take. But I guess it's important actually that you have no undefined behavior anywhere in the program. And I just wanted to clarify that that's actually what happens, that your programs are guaranteed UB-free everywhere, not just on the execution path.
So the guarantee that we do give over here is the program is indeed UB-free only on the execution path. You can take a different input, and we don't guarantee that it's going to be UB-free. It can hit whatever we want. As far as EMI is concerned, I am not super aware of that. Maybe Song can give more insights on it.
Basically, what we have ensured is that given the specific input, the execution of that program is UB-free. But if you give it some random input, we cannot guarantee that because UB is a dynamic behavior. And for those like basic blocks that has not been reached, either at the runtime or at compile time, we want the compiler to infer them, to infer some information like the reachability, like define use chains from them so that it can perform some like stressful optimizations, aggressive optimizations, or even infer some information that it thinks useful, but actually it's buggy, and so that we can find the bug. Thank you.
All right, I think we have time for at least one more question.
Hi, thank you for the talk. I'm a PhD student from Boulder. I'm not sure I understand correctly, but in your slide, you said that you're generating a function with a single pass symbolic execution. Is there any like restrictions due to the single pass symbolic execution? For example, if you use the original symbolic execution to generate the function, can you generate more complex functions than now?
I'm not sure I understand the question, sorry.
I mean, like, is there any some like the behavior restrictions on functions? So, but because of the single pass symbolic execution. So yeah, that's my question.
Yeah, sorry, you can go first. Yeah, we did try multiple path execution, but again, it's just like more constraints on the SMT solver, and it was a little more intractable for it to solve. That's why we decided to stick with single path for now.
It is also possible to like use full like symbolic execution to generate the program. But one thing is you have to model the constraints for different paths. And the second thing is you have to consider the performance of the solver. For a full symbolic execution, I don't think the solver can handle it for a large program. Even for a small function, I don't think it can handle it very well, especially when you add in more like features, like vectors, like pointers, like arrays, indexing that makes the solver very, very like stressful. But I think it's also possible, I'll see. Yeah. Thank you.
I think we can take one more question while the next speaker sets up. Actually, I had one question. It seems believable that you can take an arbitrary CFG and reify it using goto. But if the particular CFG is able to be synthesized using while loops or for loops or something, are you able to recognize that? Or do you always just use goto?
We do have some support for like having more reducible loops in our program as well.
Okay. All right, let's thank the speaker again.